clicked for JWST's little red dots. You're in the right place. These compact, intensely red sources in the early universe don't behave like young galaxies. They look like black holes that grew too fast, too soon. Why are they so red, so small, and so powerful? In the next minutes, we'll decode their infrared fingerprints and show how these objects challenge the slow, star-first growth story. Stay with me as we test the heavy seed idea, direct gas collapse, against what Webb actually saw, and see why the first chapters of cosmic history might read very differently than we thought. If these dots were normal baby galaxies, their light would smear out and skew blue. Webb, instead, keeps finding pinpricks that glow deepest red and refuse to spread. Why would a newborn universe prefer a spotlight over a glow? Webb's infrared eyes shift our expectations. Light from the first billion years is stretched by cosmic expansion, so photons that started in the ultraviolet and optical arrive in NIRCam and MIRI as longer wavelength signals. Young galaxies should show clumpy, extended star-forming regions, with blue rest UV starlight sliding into the shorter infrared filters and a modest rise toward the red from dust. You'd expect a patchwork, knots of stars, nebular lines on top of a young continuum, and sizes that reflect turbulent, growing disks or puffy protospheroids. Instead, the objects lighting up the images look concentrated at the diffraction limit and brighter in the reddest bands than the standard models predict. That mismatch piles up. Their colors climb steeply as you move to longer wavelengths, not by a little, but by enough to imply either extreme dust or a different power source. Their flux spikes at specific bands, then drops across a break that lands where you'd expect the Balmer or 4,000 angstrom feature once redshifted. And right where a smooth stellar spectrum would gently roll, you see broad humps and line-dominated bumps that don't fit simple, continuous star formation. If starlight dominated, a mix of hot, short-lived stars would fill in the blue and keep the continuum flatter. Look closer, and the spectrum tells on itself. The continuum rises like a ramp toward the red, signaling warm dust heated by something compact. Breaks are strong enough to mark a mature stellar population only if ages were higher than the universe allows at those redshifts, which hints at another cause: reprocessed light from a central engine. The lines give it away. Emission features consistent with broad H-alpha, strong, O3, and helium-2 show up at the expected observed wavelengths for high redshift, and their widths imply gas moving at thousands of kilometers per second. That's the signature of deep gravitational wells feeding at high rates, where radiation pressure brushes up against the Eddington limit and sometimes pushes beyond it for brief spells. Think of a nighttime city. A thriving galaxy should look like a skyline, many lit blocks spread across a few pixels. These sources behave like a single blinding spotlight on a rooftop. The light comes from a compact engine, not a neighborhood of stars. Webb's sharp imaging pins down sizes that back this up, effective radii measuring tens to a few hundred parsecs. At the same epoch, typical galaxies extend over kiloparsec scales, with light profiles that fall off smoothly. Here, the light refuses to spread, clinging to the center as if gravity and energy are coiled into one tiny region. Redshift estimates from their colors place them in the early universe, and the line detections point to accretion. The energy budget works out only if a black hole, not stars, is doing most of the work. That leads to a striking implication. If a central black hole powers the emission and the host remains this diminutive, then the usual relationship between black hole mass and galaxy mass is upside down. The hole could rival or even exceed the stellar mass enclosed by that tiny radius, a ratio that local galaxies reserve for the rarest extremes. So the mini payoff here is simple. The infrared fingerprints match buried quasars more than ordinary galaxies. These little red dots behave like overgrown black holes tucked inside undergrown hosts, their dust and gas re-radiating energy in the reddest bands that Webb can see. And if they already act like massive engines in a universe still learning to build galaxies, the slow growth playbook starts to slip. So where did the extra mass and fuel come from so early? And why did it find the center first? If black holes looked fully grown when the universe was a toddler, maybe they didn't start small at all. What if they were born heavy? You've heard the usual starting point. light seeds from the first massive stars. Those population 3 stars live fast, shed metals into their surroundings, and die as black holes weighing maybe 10 to 100 suns. That route can work if the clock runs slow. It doesn't. To hit the billion solar mass mark by redshift greater than 7, a seed like that has to feed almost non-stop, skimming the Eddington limit or even overshooting it for stretches, and it has to keep its fuel despite outflows that heat, stir, and blow gas away. Feedback fights you at every step, and mergers don't solve the pace on their own. Heavy seeds offer a shortcut. Instead of starting with a tiny remnant, you begin with a black hole already in the 10,000 to million solar mass range. How do you get one? Strip down the conditions so gas can fall straight in. You want metal-poor gas so it can't cool into small, dense clumps that fragment into stars. You want a strong Lyman, Werner radiation background from nearby star-forming regions to break apart molecular hydrogen, which otherwise acts as the coolant that triggers fragmentation. With H2 suppressed, the gas stays warm, around 10,000 Kelvin, and collapses smoothly. Inflows stay rapid because nothing turns into stars fast enough to dam the stream. Under those rules, an atomic cooling halo with a total mass of 10 to 100 million suns becomes a funnel. Gas sinks toward the center at 1/10 to 1 solar mass per year, forming either a bloated quasi-star, a hydrostatic envelope powered by a tiny, growing core, or a massive, pressure-supported disk that transports angular momentum outward and mass inward. The object at the center grows so quickly that radiation can't escape efficiently. Much of it is trapped and advected inward, keeping the collapse going until a black hole forms with a head start. No mature stellar bulge, no extended disk, just a newborn engine embedded in dense gas. Simulations that follow gravity, gas dynamics, and radiation show what this looks like in light. Even at early times, the spectra lean toward an AGN-like continuum in the rest UV and optical, with hard ionizing photons that light up lines from helium and oxygen at high ionization states. When redshifted into the infrared, that mix produces the steep, red continua and the broad features you expect from gas orbiting close to a deep potential well. Models also predict compact morphologies because the emission comes from a tiny central region, with the surrounding starlight still faint and young. So what can Webb test right now? Line widths first. Broad components with thousands of kilometers per second spread point to fast-moving gas near a massive, compact source. The He2 1640 angstrom line matters because it needs hard photons. Strong flux there favors an accreting black hole over normal star formation. If you can add X-ray detections from other observatories, even better, though heavy obscuration may hide the core. Measure how the black hole mass stacks against the stellar mass in the host. A large ratio signals a heavy seed or rapid early growth. And check the shape. Tight sizes with no bright, extended stellar outskirts match a central engine dominating the light. If heavy seeds form, we should see systems where the black hole outweighs the galaxy by a hefty margin. Several of the little red dots line up with that expectation, acting like engines first, neighborhoods later. Direct collapse neatly addresses the speed problem, the tiny sizes, and the AGN-like fingerprints that don't sit well with a star's first path. Which pushes us to redraw the first pages of structure formation, and then ask what that new map predicts for the next set of targets Webb will chase across the high redshift sky. Heavy seeds flip the script. Early black holes may have formed large, making the first galaxies grow around them. That turns starlight into a side effect of engines already running hot. If that's right, galaxy assembly follows gravity's shortcut, not a slow ladder from stars to bulges to black holes. Watch for the next JWST spectra and multi-wavelength follow-ups. Each new red that will test whether direct collapse is rare, common, or only part of an even stranger origin. Keep an eye on line widths, compact sizes, and black hole to host ratios. If gravity built engines first and cities later, what else are we reading backward?
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.